let's practice using our equilibrium constant framework for analyzing equilibrium reactors. And so in this in-class problem, we're dealing with a system in which we're producing carbon disulfide by reacting solid carbon with sulfur gas. We're told the Gibbs energy, standard state Gibbs energy of the reaction, and also the standard state enthalpy of the reaction. We're told the reaction occurs at a pressure of 1 bar, and that there's not really any sort of oxygen or other species that would lead to a side reaction. Assuming that the reactor is fed with a stoichiometric amount of carbon and sulfur, what we want to do is we want to calculate the equilibrium percentage conversion of the sulfur at 2 different temperatures. And so based on the information in this problem statement, I want you to pause the video here, and I want you to sketch out a process flow diagram for the system. So based on the information in the problem statement, we could sketch out a problem process flow diagram that looks like this. So here's our reactor. It's operating at a pressure of 1 bar and either a temperature of 750 or 1000 degrees Celsius. All right, for our basis, we're told that the reactor is fed with equal molar amounts of carbon and sulfur. So for our basis, I just assumed that we had a feed flow rate of 2 moles per second, so that for the carbon and sulfur, their molar flow rates would be 1 mole per second. Okay, and so we know what's going into the reactor, but as far as what's coming out, we don't know the molar amounts, and in the end, what we want to calculate is the equilibrium conversion of that sulfur. Okay, all right, and so here's the reaction that's occurring. All right, so we have carbon solid, sulfur gas, and they proceed in an equilibrium reaction to form carbon disulfide. All right. Okay, for the conversion, it's defined like this, where essentially we're just taking the difference between the sulfur that's fed in and the sulfur that comes out, divided by the sulfur it's fed in. And we're also told the Gibbs energy of the reaction and the enthalpy of the reaction as well. Okay. Now, before we proceed with our analysis, we need to make a few assumptions about the system. Okay. As you could tell from how I defined the system here, I defined it as an open system. Potentially, you could also, if you wanted to, instead define it as a closed system. In the end, it shouldn't affect the conversion value that you calculate. All right, I defined this as an open system. I'm also going to assume that we're operating at steady state. All right. When it comes to other sorts of assumptions, here we're kind of dealing with we are dealing with a heterogeneous reaction. The carbon's in the solid phase, while the sulfur and the CS2, those are going to be in the gas phases. So for the solid phase, we're going to assume that it is an ideal solution, such that the activity of the solid phase is just equal to the mole fraction of carbon within that solid phase, right? So you got to be careful with this definition here, and we'll talk more about it later. Okay. All right. The next assumption I want to talk about has to deal with the gas phase components. And so in the gas phase, we have both the sulfur and the carbon disulfide. And so what we'll do here is we'll assume that our gas phase is an ideal gas mixture, such that the activity of the species in the gas phase is going to be just the partial pressure of that species divided by the standard state pressure, and we can relate the partial pressure to the mole fraction as well. Okay? All right, so those are the assumptions we're going to make. Now, as far as, figuring out how we could relate the conversion to the temperature of the reactor, the way we're going to do that is going to be by relating the equilibrium constant of the reaction, so K, to the activities of each species. Of each species in the system. Okay? All right, so what we want to do is we first want to define the activities for the carbon, sulfur, and carbon disulfide. So for the carbon, so we'll say the activity when it's coming out of the reactor. Generally, we would describe it as, for any sort of solid solution, the activity coefficient for that species times the mole fraction of that species as well in the solid phase. But because we're assuming that the solid phase is an ideal solution, this activity coefficient is just going to be equal to 1. So because it's ideal. For the sulfur, it's in the gas phase. So we made the assumption that the gas phase is an ideal gas. So that's how we would write its activity for the sulfur. And for the carbon disulfide, it's a similar sort of form. CS2P over P naught. Okay? All right. And so those are our activities. And what we know is that the equilibrium constant is just going to be a product of the activities raised to their stoichiometric coefficient. Okay? All right? And so here, for CS2, the stoichiometric coefficient would be a positive 1, while for the reactant side, for carbon, it would be -1, and for sulfur, it would also be -1. And so as a result, we find that our equilibrium constant would take on this form. CS2. So that's just 1. And for carbon and sulfur, because they have -1, theirs is going to end up on the bottom. 2C. And just to avoid confusion, I'll put the absolute magnitude symbol there. Okay. And so these are also 1. All right. So what we could do now is we could plug in our different activities into the equilibrium constant equation. So what we get here is Y2 CS2. And I'll put the P over P naught here. And then we have Z 2C, Y 2S2, P over P naught. Okay? We can now simplify this equation, right? This P over P naught cancels out. So we'll find that there's no pressure left over in our equation anymore. The other sort of thing I want to point out is the solid state mole fraction of the carbon. When it comes to the carbon, it's the only species that's in the solid state, right? And so because it's the only species in the solid state, the mole fraction of carbon is 1. And so this term right here is actually just going to be 1. So, and that's because carbon is only solid. All right. So because the carbon mole fraction is 1, basically its influence on the equilibrium constant goes away. And really all we're left with is just the mole fraction of the CS2 divided by the mole fraction of the sulfur. Right? Those are the only terms that affect the equilibrium constant. And so the way we're going to get these mole fractions is from doing material balances. So this is going to bring us back to doing the things that you had to do back in MEB1.